Okay, so now, okay, we've always looked at having the last example we looked at having two payments to pay off a debt. And what I want to look at in these next examples, I have four examples I'm going to go over with you, is if you have to pay a debt back in installments, or in other words, in equal payments, okay, each month. So when you have a student loan and you graduate, you have this grace period where you don't have to pay it back. I believe it's 6 months. Then after that, you have to start making regular scheduled payments. So what this is going to look at is if you have multiple payments at different dates, right, but they're the same value, they're always $500, but it might be 1 month in the future, then a month after that, then a month after that. How much do those payments need to be to pay off this debt that you currently have? Okay, so if we look at that in terms of a graph, we're here today, and you've got a student loan of $25,000, let's just say. So if you were to pay it off every single month, June, July, August, September, October, November, December. We're not going to go into an example that has, 20, 30 payments. Usually when you do that, you use something that's already been made, whether it's in Microsoft Excel or use a computer for it. But what we're looking at here is how much do each of these payments need to be, if they're the exact same payment each time, to pay off that initial debt of $25,000. Right? That has to take into account, remember, future value with interest. Okay, starting with this present value in this example of $25,000. So I'm going to start off with an example just to show you kind of how I would approach these calculations. Let's look at an example of these equivalent payments. So May is due to make a payment of $1,000 now. Instead, she negotiated two equal payments, 1 year and 2 years from now. Determine the size of the equal payments if money is worth 8% compounded quarterly. So, what we know is the payment that she's looking at is $1,000 right now. But instead, she wants to make payments in the future. All right? So, if we start with our graph, we have right now, call it year 0. And the amount her debt is worth is $1,000. But instead of paying it off right now, she wants to pay it off in two equal payments. Keep in mind, equal payments. One being 1 year from now, year 1, and one being 2 years from now, year 2. So this is payment number 1, and this is payment number 2. So the amount that she wants to pay at those periods of time is the same. But what you'll notice, okay, when we're looking at this question, we have to have a focal date. So our focal date is that we know $1,000 now. Okay, we know that that's how much she has to owe. So the focal date is year 0. So we have to actually take these two payments that she would have to pay and discount them backwards in order to figure out what they need to be, right? Because we have to pick a focal date so that our money is worth the same amount, all right? So the amount that she owes today is $1,000. And that has to be equal to our two payments, right? And since we're moving into the past, we need to find present values. So it's the present value of payment number 1 plus the present value of payment number 2. Okay? So if we write those out as their full formulas, present value 1 is equal to the future value, or the amount, okay, at year number 1, divided by 1 plus the periodic interest rate to the exponent n, and that n is the total number of compounding periods for that payment, plus payment number 2, which is 2 years from now, okay, future value number 2, divided by 1 plus that periodic interest rate raised to the exponent n, the number of compounding periods. So keep in mind, remember, these future values are actually the payments that she would give at each one of these years, right? And since they're equal payments, what that actually means is that that future value for year number 1 has to equal the future value of year number 2, because that's the future value, remember, that's the amount of money that May would be paying at year 1 and at year 2. Okay, so they have to be equal. And remember, when we're trying to find a variable, okay, I like to call them something. I'm going to just call them x. All right, so I'm going to substitute that into this equation. So we have $1,000. Okay, and remember, that's today. That's at year 0. That's how much her debt is worth. And that'd be equal to her first payment, x, divided by 1 plus the periodic interest rate to the exponent n. Remember, that's n is different than the n for the second payment because they're different years apart. Plus, again, substituting x divided by 1 plus the periodic interest rate raised to the exponent n again. Okay? So I'm substituting those in, and what you'll notice is now I need to solve for those, and we'll end up at the end with an algebraic expression where we can solve for x, okay? Because I'm calling that future value, okay? So we now need to find the remainder of the variables, the periodic interest rate, as well as the number of compounding periods for each one of these payments. So looking at payment 1, we know that the interest rate, nominal interest rate, is 8%. That's provided up here in the question. We also know that it's compounded quarterly. That'll be next. So our nominal interest rate is 8%, which is equal to 8 divided by 100, removing the percentage sign, or 0.08. Our number of compounding periods, it's given as quarterly, so that means our value for m is 4. So our periodic interest rate, and remember, this is the same periodic interest rate for both of the payments because it didn't change in the question. So our periodic interest rate is equal to j divided by m, which is 0.08 divided by 4, which is equal to 0.02. Now for this question, for this payment, the number of compounding periods is equal to the number of years multiplied by the number of compounding periods per year. It's simple. We're given in this question, right, the difference from here to here is 1 year. So n is equal to 1 multiplied by 4, the number of compounding periods per year, and we get an answer of 4. Now, looking at payment number 2, we know the periodic interest rate is the exact same, 0.02, because it doesn't change in the question. We also know that the the number of compounding periods per year, m, is also the same, 4. But our number of compounding periods, n, okay, it's equal to the number of years multiplied by the number of compounding periods per year, m. And in this case, we're at year number 2, which means we're 2 years ahead from this initial payment this initial debt, which is worth $1,000 today. So that means n is equal to 2 multiplied by the number of compounding periods per year, 4, which gives us a value of 8. Okay? So now we have all of the data. The only thing we don't have in this equation you're going to notice is x, so we're going to solve for that. All right? So substituting all of these values into this equation, we have $1,000 is equal to x divided by 1 plus 0.02. Again, that is raised to the exponent 4 for this payment, plus x divided by 1 plus 0.02. And in this instance, it's raised to the exponent 8 for the second payment. Okay? So I'm going to move this equation just to the next slide so we can continue the calculation. So, like I said, we had $1,000, and that was equal to x divided by 1 plus 0.02 to the exponent 4, plus, again, x divided by 1 plus 0.02 to the exponent 8. So I'm going to simplify this. All right, what I'm going to do is I'm going to solve for this bracket in the denominator. All right, so that means we have $1,000 is equal to x, and if you solve for the denominator, you get, I'm rounding, 1.0824 plus x divided by, again, solving for the denominator, you get 1.17166. Okay, so I have a little more decimals just because of how the numbers worked out. So now you want to simplify these. Okay, so remember from back when we did fractions or when we did algebra, when you have something like x on the numerator, that's the same as having 1 multiplied by x, right? So what that means is that we can actually solve for the two fractions in both these, have them as decimals, in order to solve for the next step. So what I'm going to do, right, is picture, remember, since this is equal, same as 1 times x, I can actually solve for that fraction. So in the next part of my equation, I'll have $1,000, and that's equal to, first one, the fraction, 1 divided by 1.0824, and we get 0.9239 multiplied by x, right? All I've done is solve for that fraction, the 1 divided by 1.0824, okay? Plus the second one, which is 1 divided by 1.17166, and I got 0.8535x. Okay, so all I've done is simplify those fractions into decimals, so now we can add them together and then solve for x. So if I add these two items together, 0.9239 plus 0.8535, because remember, they have the same term x, so we can add them together to simplify. We get $1,000 is equal to 1.7774x. So now, remember back from the last course, when all you have left is to solve for x. And to do that, you need to have x by itself. So we have to divide both sides by 1.7774. So that on this right side, 1.7774 divided by itself is just 1, so it cancels. And we're left with just x, and that's equal to $1,000 divided by 1.7774. And we get $562, and in this instance, 62 cents. You'll notice my answer says 64 cents. And that is a consequence of rounding, right? So showing you this example, I rounded each time. If you kept that number unrounded in your calculator, and remember you can use the button that says answer, and it will actually use the number that's been calculated in the calculator, and you'll get a more exact answer. But they're close enough. When I see your answers on test, I'd also realize it's close enough. But basically, what this is telling you when you get this answer is that if you paid $562.62 1 year from now and 2 years from now, you would pay off this $1,000 debt that you had. Okay? And it makes sense that instead of it just being 2 payments and it's $500 a payment, right? Because I'm going to pay half of it in a year and I'm going to pay the other half in a year. You'll notice this value is higher, and the reason it's higher is because you have to include the interest that's being accumulated by you not paying it off immediately, right? That comes back to our conversation on the time value of money. So let's look at another example. Olympia owes $4,000 in 4 years. She wants to repay the debt earlier and plans to make 2 equal payments, one in 16 months and one in 28 months from now. Determine the size of the equal payments if money is worth 6% per annum compounded monthly. So, again, I'm going to start with a graph. Okay, so we're at year 0. Okay, and in 4 years, so year 4, Olympia owes $4,000. Now, for whatever reason, maybe she feels she can save up to pay it off earlier, or maybe she came into some money or something, and she wants to pay it back earlier than the date that it's due. So she wants to do it in 2 payments. The first one is 16 months from now, and the second one is 28 months from now. And they're equal payments. So we have payment 1. We don't know what payment 1 or payment 2 are. But we do know that her total debt's worth $4,000. So in this question, you see that our focal point is going to be when her debt is actually due. So that means that we have to find the future value of our 2 payments so that it's equivalent to $4,000, or the amount that she would be due in 4 years. Okay, so just like we've done, except in the previous question, we worked back and did a present value calculation. In this instance, we're doing it as a future value. Okay, so keep in mind a couple items that are noted in the question. She noted 2 equal payments. So just like in our previous question, right, we need to figure out what these payments are, and they're both going to be the same. So I'm going to call them, let's call this one future value 1 and future value 2, right? Because we're going into the future, we need to do future value calculations. So when we look at this, our payment, or our total amount of $4,000 at year number 4, has to be equal to our future value of our first payment, 16 months from now, plus the future value of our second payment, 28 months from now. So if we write this out, the future value formulas, we have $4,000 has to equal present value of that payment multiplied by 1 plus the periodic interest rate raised to the exponent n. Again, that's the number of compounding periods for this payment, plus present value payment 2 times 1 plus that periodic interest rate, all raised to the exponent n. Again, the number of compounding periods for this payment. So what we know is each of those present values is a payment that she has to make, right? And they're equal. So just like our last question, the first payment, or the first present value, has to equal the second present value 2. And I'm going to call that x. Okay, so that equals, those equal sum term x. All right? So I'm going to substitute that into this equation, and we're left with $4,000 must equal x, or whatever her payment is, times 1 plus periodic interest rate to the n, plus x times 1 plus the periodic interest rate to the n. The only difference between these will be the number of compounding periods per year. So again, in the question, like I've said, we're given that it's 6% per annum and compounded monthly, and it's only provided once. It doesn't change. So that means that our number of compounding periods per year and our periodic interest rate will be the same for both of our payments, right? So let's look at payment 1. Our nominal interest rate, J, is equal to 6%, which is 6 divided by 100, removing the percentage sign, which is equal to 0.06. Our number of compounding periods per year is provided in the question that it's monthly, so that means M is 12. So our periodic interest rate is J divided by M, which is 0.06 divided by 12, which is 0.005. Some of you might also have it in your calculator as 5 times 10 to the negative 3 if you're following along. All right? Lastly, our number of compounding periods, N, is equal to the number of years multiplied by the number of compounding periods per year. So in this question, for this first payment, it's 16 months from now, all right? But it's actually, the period we're talking about is 4 years from now. So 4 years multiplied by 12 months per year is actually 48 months. So we want to find the difference from this period in time to this period in time. So that means we can find that total number of months because it's 48 months, the period at the end, minus how many months have gone by, right? 16. So minus 16, and we get that we actually need to find the future value 32 months into the future from this period in time. So if we substitute that in, n is equal to 32, and again we have to convert the months to years, so I'm going to divide it by 12, that's 12 months in a year, multiplied by the number of compounding periods per year, which is 12. So again, you can do this in your calculator, or you can notice that there's a 12 in the numerator and a 12 in the denominator, and they cancel. And you end up getting a value for n of 32. Now, looking at payment 2, remember the periodic interest rate is the same, 0.005, and the number of compounding periods per year is also the same, of 12. The difference is going to be the value for n. So n is the number of years multiplied by the number of compounding periods per year. And we know in this case, it's 28 months from now. So we know, again, that where the focal date is year number 4, which is 48 months from now. So to figure out how many months we have to move forward for our future value, we have 48 months minus the months that have already elapsed, 28. So that means we have to go 20 months into the future from this period in time in order to get to year 4. So if we substitute that value in here, we get n is equal to 20. And again, we have to convert this to years. So we divide it by 12. And we multiply it by the number of compounding periods per year, which is 12. And just like for payment 1, these 12s cancel. And we're left with a value of n of 20. So now we have all this data, we can substitute it back into our equation. So we have $4,000 is equal to x, this is the first payment, times 1 plus 0.005. And that's raised for this payment to the exponent 32, plus x again, times 1 plus 0.005. And in this instance, it's raised to the exponent 20, right? Because we're moving 20 months or 20 compounding periods into the future. So if you simplify these, we get that 4,000 is equal to 1.173 times x. All I did was simplify everything in the brackets, plus 1.105 times x. Okay? So in the previous example, you had it being divided. In this instance, it's being multiplied. And again, since they both just have the same term x, you could add them together in order to simplify. So you have 4,000 is equal to, if you add those together, you get 1.173 plus 1.105. You get 2.278x. So now, just like we've done for algebraic equations, we need to solve and just have x by itself, because x, remember, is equal to our payments, right? And they were equal payments. So our present value numbers for both payment 1 and payment 2. So to do that, you have to divide both sides by 2.278 to remove it from the right side of the equation. So now 2.278 divided by 2.278 is just 1. And we're left with solving for x, which is our payments, and we get $1,755.93. Okay? So that means that Olympia can pay $1,755.93, 16 months and 28 months from now. And because, remember, of the time value of money, that pays off her $4,000 loan. So she's saving money by paying it off earlier. And again, the reason she's doing that is because she's not having to pay as much interest on all of that money because she's paid it in advance. Okay, our second last example for equivalent payments. What is the size of the equal payments that must be made at the end of each of the next 5 years to settle a debt of $5,000 due in 5 years, if money is worth 9% per annum compounded annually? So this is a little bit larger of a problem just because we have 5 different payments this time over that period of 5 years. Again, they're all equal though. So just like we've done in the past, that value of payment, which we've called x in the past, will be the same. So starting with our graph, okay, so we are right here, year 0. We've got years 1, 2, 3, 4. I did a bad job drawing this, so I'm going to do year 5. And each year, at the end of each year, we're going to have a payment. So we're starting at year 0. At the end of year 0, we're at year 1. So we have a payment here. So we'll call it payment 1. Then at the end of year 1, we're at year 2. So we have payment number 2. Payment number 3 at the end of year 3. Payment number 4 at the end of year 4. And at the end of year 5, the same time that the $5,000 is due, we'll have our last payment, payment 5. Okay, so we have to make 5 separate payments here. All right, and it has to equal the $5,000 that's due 5 years from now. So that means our focal date is at year number 5, right? Because we know that our total debt is equal to $5,000 at this point in time. So that means each of these payments has to be translated to a future value. Okay? The only exception being our final payment doesn't have a future value, right? Because it's paid at the exact same time. So it's already at the same time frame as the $5,000. So what that means is when we write our formula, right, if we're looking at it, so our total amount we have to pay, $5,000, has to be equal to our 5 payments, right? And remember, since we're going into the future, these are all future value calculations. So we have the future value for payment number 1, plus the future value for payment number 2, plus the future value for payment number 3 and payment number 4, plus you can call it the future value of payment number 5, but it's at the same time as the $5,000. So remember, and in every question, we're trying to get it, all of our dollar values to be at the same period in time. So we're comparing apples to apples, right? So that last one, I'm just going to call it X. Because like I said in every one of our other questions, our payment is exactly the same. So our final payment, I'm just going to call X. So if we expand this formula, we get $5,000 is equal to each of our future value formulas, which is the present value of item 1, or payment 1, times 1 plus the periodic interest rate to the exponent n. I'm going to call them n1, n2, n3, and 4 just to represent the year that you're in, plus present value for payment 2 times 1 plus I to the n. I'm going to put n2 because it's a different number of compounding periods, plus present value 3 times 1 plus I to the exponent n. I place a 3 there, plus the present value for payment 4 times 1 plus I to the n 4, and I plus x. Now remember, since all of these payments are equal, that present value at each period in time must be the same. Okay? So what that means is present value 1 has to equal present value 2, present value 3, and present value 4, which have to be equal to that same final payment. We're paying the same amount of money 5 times. So they'll have to equal x. So each of those is equal to x. So now if I rewrite that formula, we have 5,000 is equal to the first payment, x, times 1 plus I to the n1. All the rest of the terms are the same. I'm just substituting x in for each of these. Whoops, made a mistake. So for payment 4, x times 1 plus I to the n4 plus x. Okay, so this formula looks very daunting because it's such a long formula, but really all we're doing is we're doing a future value calculation for each of these items. Okay, so now for each of these payments, remember again in this question, we're only given one interest rate and then it's compounded annually for every single one of them. So that means your number of compounding periods per year M and your periodic interest rate I will be the same for all of them. So calculating those first, all right, we know that our nominal interest rate in the question is 9%, which is equal to 9 divided by 100, removing the percentage sign, which is 0.09. M is really simple. The number of compounding periods is annually, so M is just 1. So that means the same, okay, your periodic interest rate, I, is J divided by M, which is 0.09 divided by 1, which is just equal to 0.09. So those terms will not change for any of them. Again, the only thing that changes is going to be your total number of compounding periods N for each one. All right? So now for each of these 4 payments, I'm going to calculate N. Okay? So I've got N1, okay? In general, remember, it's the number of years multiplied by the number of compounding periods per year. And in this case, it's just the number of years, right? Because M is 1. So if we want to look at calculating each one, first one, N1, okay? So for this first payment, it has to go from year 1 to year 5, so 4 multiplied by 1, the number of compounding periods per year, which is 4. N2, okay, from this case point here, we have to go 3 years. So we have 3 times 1, which equals 3. For N3, we've got to go 2 years, right? Because now we're at year 3. So it's 2 times 1, which equals 2. And for N4, our fourth payment, we're only moving 1 year, right? Because we're doing it in year 4. So 1 times 1 equals 1. So now we have all of the values, and we just need to substitute them into this formula. So it's going to look like there's a lot of numbers in this formula, but keep in mind, I'm putting it all into one formula, and then we're going to simplify it rather quickly. So we have $5,000 is equal to X times 1 plus our periodic interest rate for each payment is 0.09. And for N1, remember, it's the exponent 4. Plus x times 1 plus 0.09 again, and N2 was equal to 3. Plus x times 1 plus 0.09 again, and N3, remember, was 2. Plus x times 1 plus 0.09, okay, and that is also the exponent 1 for the fourth payment. And then the last term is just x, okay? So the easiest way to look at this is to simplify each one of these, okay? So I have 5,000, and all I'm doing is I'm doing everything in the brackets and with the exponent first, okay? So 1 plus 0.09 to the exponent 4, that's 1.412 times x. For the second one, it's 1.295 times x. For the third one, it's 1.188 times x. And the fourth one is 1.09 times x. And the final term is just x. And remember, when it's just x, it's the same as 1 multiplied by x. So now we've got 5 terms with numbers in front of them, all x. So we can add them together in order to simplify. So we can add the 1.412 plus 1.295 plus 1.188 plus 1.09 plus the 1 for the last payment. Okay, this is one of the more complicated examples because there's so many payments. Okay, but as you can see, there's a lot of items in this formula, but it's following the same pattern. So if you add all those together, 1.412 plus 1.295 plus 1.188 plus 1.09 plus the 1 for the last payment, right? Remember, because x is just same as 1 times x, you get that 5,000 must equal 5.985 multiplied by x. Okay? If you do that, all right, now you just need to solve for x. And remember, you do that by removing the 5.985 from that side of the equation by dividing both sides by 5.985. So on the left side, 5,000 divided by 5.985, you get $835.42. And that's equal to just x, because 5.985 divided by 5.985 is just x. So what you'll notice, again, just like in the past examples, this is actually off by 4 cents because my answer said 835.46 on the bottom left here. And that's just because of rounding. Again, doing this as an example, I'm rounding more to show you each individual step. If you did it all on your calculator in one time, you get just a slightly different answer, off by a few cents. Okay? All right, so we're at our final example for this lecture. Scheduled debt payments of $750 due 7 months ago, $600 due 2 months ago, and $900 due in 5 months are to be settled by 2 equal replacement payments due now and 3 months from now. Determine the size of the equal replacement payments at 9% per annum compounded monthly. All right, so what we see here is you have 3 debt payments that you were supposed to pay, and instead you want to consolidate them into 2 payments at a different period in time. So I'm going to start this again with my graph. And I saw when I read the question that I do have some payments before today, where we are, and some after. So I'm going to place today here in the center. And I'm going to start looking at the payments and where they are. So your first debt payment was $750, and it was 7 months prior to today. Okay, so that was $750. Your second payment was $600 2 months ago that you didn't pay, or that someone didn't pay. And your third payment is technically not due for another 5 months. So plus 5 months, and that value was $900. And you want to replace these by 2 equal replacement payments. One today, so we'll call that payment 1, and 1 3 months from now. So plus 3 months, I'm going to call that payment 2. So we have 5 different payments being shown, the 3 that you were scheduled to pay, and then the 2 that you're trying to consolidate that into. And one of them is actually listed as today. So a good focal point to select would be today, right? Because that payment you do not have to do a present value calculation on because we're already at the focal date, right? And remember from the past questions, these are all equal replacement payments. And since they're equal, that means we usually set that value to something like x. So looking at this problem, we actually have 2 payments that would have to move into the future, or you do a future value calculation for, and 2 payments that we have to go into the past, and we have to do a present value calculation for. Okay? So remember, when we look at this formula, we're trying to balance this out. We're trying to take your 3 payments and consolidate them to 2. So we want them to be equivalent if our time, assuming using time value of money, equivalent at the period of time, which we've called today. That's what I had highlighted in purple. So in other words, your scheduled payments has to equal what you're trying to consolidate them into, or what they called it in the question, the replacement payments. Okay? So our payment value, right, the amount of the equal payments, I'm going to call that X. Okay? So the value of the replacement payments, each one, remember there's two, we're going to call that X. So now I'm going to look at this formula. My scheduled payments were these first two, right, that are future value calculations, as well as the payment that hasn't passed yet. That was a present value calculation. So I need to substitute those in. I would have the future value. Well, I'm going to switch colors. That should keep it consistent. The future value for payment number one is $750, plus the future value of payment number two, this $600 that you didn't pay, plus the present value of your third payment that was due, the $900. That has to be equal to what you're paying in these two replacement payments. So our first payment was due today, so we don't have to do a calculation. That payment is just X. And our second payment would be due in 3 months from today, so it's going to be a present value calculation. So I'll call it present value calculation for payment number 2. Okay? So one more item to note before I substitute in the equations for each. Again, it's given as 9% per annum interest compounded monthly. Interest rate does not change. That means your periodic interest rate and your number of compounding periods per year, the M value, will be the same for every one of these calculations. All right, the only thing that changes, yet again, is the value of N. Okay? So I'm going to just substitute the formulas in for this. So future value 1, that's equal to the present value at time 1, all right, multiplied by 1 plus the periodic interest rate to the exponent n, plus the present value for payment number 2 times 1 plus the interest rate, periodic interest rate, the exponent n, plus our third payment, which is a present value calculation, and that's equal to the future value of that payment 3 divided by 1 plus the periodic interest rate to the exponent n. Again, each of these values of n are different. I'm going to label them n1, n2, and n3. That has to be equal to x. Remember the payment, because we're in time period of today, it doesn't have a future or present value calculation. That number is already considered equivalent today. We're going to add the present value of our second calculation. So the present value is equal to that future value of the payment. Okay, so future value of that payment, which remember, that is the same as x, divided by 1 plus that interest rate all to the exponent n. I'll call this n4, or the fourth compounding period. So you'll notice that instead of placing future value in here, I placed x, right? And that's because the payments are equivalent. Okay, so the payment that you're paying today and the payment you're paying 3 months from now are the same. All right? So now we have to calculate all of our values in order to substitute them into this formula. Okay, so I'm going to do this over here on the right. We'll start. We know that our nominal interest rate is 9%, provided in the question, which is equal to 9 divided by 100, removing the percentage sign, which is equal to 0.09. Our number of compounding periods per year, M, is given in the question as monthly, so that means M is 12. Our periodic interest rate is equal to J divided by M. Again, it's the same for every one of these, right, because the interest rate doesn't change. And that's equal to 0.09 divided by 12, which is equal to 0.0075, or some of your calculators will show it as 7.5 times 10 to the negative 3. Those numbers are the same. Now, we need to figure out the number of compounding periods for each one of these calculations. All right. So first, we'll do N1, N2, N3, and N4. So remember that N is equal to the number of years multiplied by the number of compounding periods per year, M. So our first instance, okay, N1, it's 7 months from today, right? That's given in our question. So that means it's 7, and we have to convert it to years. So it's 7 divided by 12, 12 months in a year, multiplied by the number of compounding periods per year, which is 12. Again, you'll see this for all of these, that the 12s will cancel. And so N1 is 7. For number 2, okay, it's 2 months from today. So it's 2 divided by 12, multiplied by the number of compounding periods per year, 12. Again, the 12s cancel, and we get an N of 2. N3, okay, notice that that third payment is 5 months, okay? Going back to our graph here, it's 5 months from today, so that means it's 5 divided by 12, multiplied by the number of compounding periods per year, 12, which gives us 5. And our last one, N4, which is the second payment that we have to make when we're consolidating and we're bringing it to our present value. That's 3 months from today. So that's equal to 3 divided by 12, multiplied by the number of compounding periods per year, 12. And again, as in all of these examples, the 12 cancels, and you get N4 of 3. Okay, so now we have all these variables. I'm running out of space on this slide. I'm going to go to the next slide, and I'm going to write out each of the variables that we need. So just copying the numbers over that we had. Remember from our previous slide, we had that the periodic interest rate was 0.0075. And our number of compounding periods, we had N1, N2, N3, and N4. And they were equal to N1 was 7, N2 was 2, N3 was 5, and N4 was 3. So remember our formula, which was quite long, okay? We had the future value, the present value for payment 1 multiplied by 1 plus the periodic interest rate to the exponent N1, plus the present value of payment 2 times 1 plus the periodic interest rate to the exponent N2, plus the future value for payment 3, right? Remember, because it was in the future, divided by 1 plus the periodic interest rate to the exponent N3. And that equaled X, right? Because our first payment was today, so we didn't have to do any formulas on that calculation, plus the future value for that second payment, which we wrote as X, divided by 1 plus the periodic interest rate, and that was the exponent N4, called that the fourth payment. So I can substitute all of these values in. The first payment given in the question was $750, so we get 750 times 1 plus 0.0075 to the exponent 7, plus our second payment, $600, times 1 plus 0.0075, and that was to the exponent N2, our second compounding period, 2, plus our third one, which is a future value, remember, because it was 5 months ahead of today, and that was $900 provided in the question, divided by 1 plus 0.0075, and that's to the exponent 5. And that had to be equal to X plus X divided by 1 plus 0.0075, and that's to the exponent 3. All right? So I'm going to just simplify each of these using my calculator. So the first item, if you multiply it out, you get $790.27. The second one becomes $609.27. And the third one becomes $867. That's just rounding. Okay, and that is equal to x plus, remember that having this x in the numerator is the same as having 1 multiplied by x in the numerator. So you can simplify that fraction. So that fraction becomes 1 divided by everything that's in this denominator, the 1 plus 0.0075, all raised to the exponent 3. So if you do that, right, you will get 0.978 multiplied by x. So now I'm going to simplify this further to have the one number on the left, and since both the terms on the right side of the equation just have x, I can also simplify those. So what you end up with, if you add them up, $790.27 plus $609.03 plus $867, you get $2,266.30, and that equals 1.978 times x, right? I just added those two terms together. So now to solve it using algebra, we need to have x by itself because x is the payments. So I'm going to divide both sides by 1.978. Okay, so if I do that, you have on the right side 1.978 divided by 1.978 is just 1. So you're left with x is equal to $1,145.75. You'll notice in my answer it's 85 cents, and again that's rounding. So by showing each of these steps every single time, you're doing a little bit of rounding, right? Each of them that has money, you're rounding to 2 decimal places. So that changes the answer. It's only 10 cents, right, if you look at the difference in the answer, but I'm just explaining why. So when I put these slides together, I didn't have as many steps when I was doing them a little bit faster, and that's why the answers ended up being a little different. Okay? So that was all I had for this lecture. I know it's a long lecture to follow on YouTube. You may want to do the first 5 examples as kind of one that you watch and kind of digest before you do the second set of examples, or you can do it all. It's totally up to you. I know that there were a lot of steps involved in these, but if you watch the videos, especially if you watch the examples in a row, you'll see that it follows the same pattern, right? Starting with a graph to figure out where all your dates are before figuring out what date you center each of your calculations on, okay? So like I said, if you have questions, please feel free to send me an email. Alternatively, in our Thursday morning tutorial at 10:30 in the morning, you can ask me questions there, and I can also try and work through some problems with you live. I will be recording those as well, so in case you miss it or can't attend, you can also just watch it later after I post it. It does take several hours for my computer to process those videos in order to post them on YouTube, so it won't be right away, but I'll do my best. Anyways, that's all I had for this lecture, so thanks everybody, and enjoy your day.